All right, welcome back to Computer Science E1. This is lecture 3, and it's our first of 2 looks at the internet. So we thought we'd start with a technological demonstration of how data actually traverses the internet, and then we'll dive in deeper and see how it actually gets from point A to point B. So most every one of you today probably sat down in front of a computer, pulled up a website, and went to somewhere.com. Or probably most every one of you pulled up your email program or your favorite webmail program, website, started typing an email, hit send, and voila. Some number of milliseconds, microseconds, seconds, minutes later, that email arrived at its destination. But what exactly is between you, point A, and the recipient, point B? Well, this black window here is an example of a Linux computer that's running elsewhere on campus. It's kind of an old school type computer whereby there's no graphical interface that I'm using. It's just a so-called command line environment or command line interface, CLI. And what that means is anything I want to do with this computer, I have to type at the command prompt. Some of you might recall DOS from yesteryear. It's a very similar idea. But there's a command on this computer called trace route, which, as the name implies, allows you to trace the route between 2 points, A and B. Well, I am going to be implicitly point A, and point B, let's say, is one of my favorite places to visit for the day's news, CNN.com. When I hit enter, my laptop here on Harvard's campus is going to send a request across the internet to CNN.com, and along the way, it's going to time how long it takes to get from point A to point B. So let's see what's in between us and CNN.com. It looks a little cryptic at first. And in fact, it seems to have paused on one line, but let's see if it makes some forward progress. And it very rapidly did. Looks like 18 steps later, 23 steps later, I'm presumably closer to my destination. Now, this is an imperfect demo, knowingly, because some of the computers between me, point A, and CNN, point B, are actually kind of hiding their identity. They're not responding to my requests using this particular tool, hence these stars here. So let's just focus for a minute on the lines that did actually appear okay here on the screen. So the very first line here actually has this thing, which we'll talk a bit more about later, but this is a numeric address. It's an IP address, Internet Protocol address, and that is my computer's IP address. What that means is that my computer, like almost every computer on the internet, has a unique number associated with it. And it's a number in the form x.y.z.w, where each of those letters is actually a number between 0 and 255, with a few exceptions. Just like a U.S. postal address uniquely identifies your home or your P.O. box somewhere in the world, so does an IP address uniquely identify computers on the internet. And we'll see later today that's actually a bit of a white lie, a bit of an oversimplification, but it'll get the conversation here started. So that address there that I've highlighted is my so-called IP address, and to the right of it are a few measurements, which we'll see in more detail in a moment. Then in step 2, apparently there's something else. It ends in harvard.edu. It's core 1 GWVL something or other, harvard.edu. And then in line 3, there's another Harvard something or other, and then we get some stars and then more. What might each of these lines in this program's output represent? Any guesses? Each of these represents some kind of computer, apparently, between me, Harvard, and point B, CNN.com. So okay, I just said they're servers. Or I just said they're some kind of computers. They're kind of a servers, but there's a special name given. And you've probably heard this before. Yeah, so it's a router. So you might have heard that there's lots of these things called routers on the internet. You can kind of infer from their name what they do. They route data from point A to point B. And for now, you can think of them as just fairly simple devices that have a really big database, a really big Excel file inside of them that say, when you get data from here, route that data over here. If you instead get data from over here, route that data over here. In short, there's some kind of table or database that says if information is destined for this address, send it that way. If it's destined for another address, send it that way, and so forth. So routers route information. Now, there appear to be multiple routers between me and CNN, and that conceptually probably makes sense, because we don't live next door, so far as I know, to CNN, so it makes sense that there's going to be a bunch of hops, a bunch of routers between point A and B. And what we can see is that apparently the first such hop in line number 2 is a router that belongs to Harvard. In step 3 is another router that belongs to Harvard. Step 4 is unclear. They're kind of hiding their tracks. But it gets interesting now in step 5. Whose router do we appear to be using in step 5 there? So Quest. So Quest is a big ISP, Internet Service Provider. They're one of the backbone providers, the really big fish out there that just have lots of bandwidth capacity, lots of routers and such that people like Harvard and even other entities connect into. From step 5, we then head to where? 6 is kind of unknown, but 7 is owned by who? So it's also by Quest, but what's kind of neat is that the sysadmins who run routers on the internet, they kind of adopted this common convention years ago where they use airport codes to identify routers' locations. So go back now to step 4, or step 5. Where is step 5? Where is that router? Probably. So Boston. So that's BST is actually not our airport code, but you can infer nonetheless. Feels like Boston. What about step 7? That's an airport code, Newark, New Jersey. So it appears that there is a connection. There's a wire. There's a satellite connection. There's some form of connection between lines 5 and 7, and that's how data is getting from one router in Boston to another router in Newark, New Jersey. Now, admittedly, there's probably another guy in the middle who's masking his identity, step 6, but so be it. It still went a few hundred miles pretty darn quickly. Step 8 seems to be, oh my God, where? Yeah, so feels like San Jose. Well, let's see. I wonder if there's another San Jose there, unless the data's really going off into nowhere there. So step 8 mentions San Jose. Step 9 mentions Newark, which makes me a little suspicious that maybe there's a San Jose that's not in California that I'm not aware of, because it feels like we should end up on the same coast here, because line 10 has us in Newark. Line 11 has us in probably... So it feels like Washington, and then line 12 feels like Washington. So we seem to be staying here on the East Coast. And then finally we get down to line 15 toward the bottom. Where does CNN server appear to be, or might be? So it feels like it might be in Atlanta, Georgia, just based on these names. Now, maybe it's a little further away because they're being a little clandestine down there. But the point is, in just milliseconds, did data get from point A, Harvard, to point B, Atlanta? How many milliseconds? Well, all of these times that I mentioned a moment ago, 28.413 milliseconds, 48.204 milliseconds. That is literally how much time it takes for internet traffic to get from here all the way down to Georgia. Any questions on this output? Well, let's see if we can't reinforce this and make the world seem an even smaller place. Instead of going to CNN.com, I'm going to go to a Japanese version of their site, cnn.co, which stands for company often, .jp. So let's see how my web browser would connect to the Japanese day's news. So steps 1, 2, and 3 seem pretty similar. Then we get a whole bunch. In fact, we made it all the way to step 17. Now let's see what we can't glisten from this. So steps 1, 2, and 3 were the same. Step 5... Anyone know what Knox.org is? You wouldn't, you shouldn't, but Northern Crossroads. This is a really big peering point whereby lots of ISPs all kind of connect in the same place so that data can then go out in different directions. So that's what line 5 is about. Line 7 is another Northern Crossroads. Line 8, actually, yeah, line 8, finally. This is not the same San Jose as before. Line 8 seems to be where? In California, and I'm inferring that because step 9 seems to belong to a company whose name is, okay, 10 gig, well, there's probably not 10 gigabit Ethernet, that's describing how fast their connection is, but Asia Netcom, something like that. But here's what's interesting, and I realize the font is big, so these lines are getting a little complicated because they're wrapping, but what's interesting about lines 9 vis-a-vis 10? Does anything jump out at you? What's that? They take a lot longer. So between 9 and 10, and in fact, they stay longer. Look at 11, 12, 13. All of those millisecond values, they've really shot up from the couple dozen milliseconds we saw a moment ago. Why? Did the internet just get slow after San Jose? Distance. What distance? What's between us and cnn.co.jp most likely? The Pacific Ocean is between us. So that probably explains the jump from like 7 milliseconds in line 8 and 73 milliseconds in line 9 to get across to the West Coast to line 10 when it's, oh my God, 186 milliseconds to get from point A to point B. And that's because point B this time is much farther away.
So this is all well and good for really big globalization. But what about you actually connecting your computer to a home network? So you realize that you probably connect to your home network either using wireless or via wired connection. We'll talk about those in a little bit more detail later. But a lot of this same thing happens close to home as well. So even when you are just sitting at your computer and you don't even have to be connected to some sort of arcane server like this, for this same sort of thing to happen, and specifically if you open up a web browser on your computer and you type in CNN.com, for example, and you hit enter, what happens? And that is what we're going to be trying to answer for you today. So basically, you can imagine that we have to contact this server, CNN.com, somehow. And David mentioned this idea of IP addresses, where every server on the internet has its own IP address. And this is really, really vital for you to understand that IP addresses, there's one pretty much, again, it's sort of a white lie, but there's one for pretty much every computer that exists on the internet today. And this allows communication between the two, because you wouldn't know, for example, how to send mail to your parents' house, for example, if you didn't know the address. And it's the same sort of thing. The IP address tells these computers and these routers how to be able to transfer data from point A to point B. But as you also probably know, we don't actually go to websites by typing in IP addresses. We haven't had to type in like 203.169.9.33 into our web browser to be able to access that website. In fact, what we do instead is to go to something like just CNN.com. Right, so instead we type in this, just something that's very user-friendly. It's a name rather than an address. So this implies that there must be some sort of system underneath it that converts from these friendly names into these IP addresses. And this system is called the domain name system. And in fact, pretty much all websites that you go to will have their own IP. They're just usually masked from you. You don't have to know what they are, but you can find out what that IP address of any particular website is pretty easily just by, well, there's a variety of tools to do this. And if you are on DOS or even if you have a Mac, you can open up the same sort of arcane window and type in some commands and be able to see the same information. But if we just type in host CNN.com, for example, we see that we get CNN.com has address 157.166.226.26. And there's a variety of other ones here as well. And why might this be? Why would we have more than one address associated with CNN.com? Right, so there's probably, CNN probably has a lot of different computers responding to people that go via their web browser to CNN.com. So when I hit enter on my web browser, it contacts this server, this server that's owned by CNN, and CNN responds by giving me a web page that I'll be able to display on my web browser. But behind the scenes, what you don't see, again, is what is happening here. Is this system, is that your computer, when you hit enter, it asks a server via this system called DNS. It asks what's called a DNS server what IP address CNN.com represents. So it is then able to find out, okay, CNN.com has this address, and then it knows, okay, now this is the actual address that I want to be able to contact, and it will go and contact that IP address using this same sort of, these hops that you saw via traceroute. So another way to think of this domain name system then is like a big address book. So just like when you know that you wanted to look up the address of a particular company because you wanted to send them a letter or something like that, you would open up an address book, or rather, an address book would work, but like the large yellow pages or something like that, and you would find that company, you would find their address, and you would be able to know where to send the mail. It's the same sort of thing. It's an analogy here on a computer system to be able to contact each of these machines and find out where we should be sending our data, where we should be sending these requests. Yes?